Last video we used a simpler warehouse example. Now we make that same world more realistic. The robot starts at the dock with a red box and a blue box, so the planner needs precise rules for what changes after each action. Suppose the robot picks up red box at the dock, but the operator forgets to remove facts that should disappear. The broken next state is now on screen. It says the robot is holding red box, but it also says the hand is empty and red box is still at the dock. That makes picking up blue box look legal too. The planner did not reason badly. It followed the operator exactly. The operator was incomplete. Strips is the language we use to specify those changes precisely. Before we write actions, we define reality. A state is the set of symbolic facts that are true right now. In this small warehouse, the initial state has 4 facts. The robot is at the dock, red box is at the dock, blue box is at the dock, and the robot has an empty hand. The goal has 2 facts. Red box must reach storage A, and blue box must reach storage B. Planning is the search for a legal sequence of actions that transforms the initial state into a state where both goal facts are true. Facts that never affect the plan, like whether the warehouse lights are on, can be left out. A strips operator is a formal contract for a type of action. It has 3 parts. First come the preconditions. Those are the facts that must already be true, or the action is not legal. Second comes the add list, which says what becomes true. Third comes the delete list, which says what stops being true. The schema uses variables. You can think of them as the robot parameter, the box parameter, and the location parameter. If we bind those parameters to robot, red box, and dock, we get one grounded action. Every required fact is present in S0, so the pickup is valid. The action fires. Watch the state update precisely. The delete list acts first. The robot is no longer empty-handed, and red box is no longer sitting at the dock. Then the add list inserts one new fact. The robot is holding red box. Everything else survives quietly. The robot is still at the dock and blue box is still at the dock. The rule is simple. New state equals old state, minus the delete list, plus the add list. Early AI researchers called this the frame problem. How do you tell a computer that picking up red box does not also change the floor, the walls, gravity, or blue box? You cannot list every fact that stays the same. That wall of unchanged facts explodes immediately. Strips solves this with one assumption. Anything not named in the add list or delete list is preserved automatically. That assumption is what keeps classical planning tractable. The model only tracks facts that actions can actually touch. What if the delete list is missing entirely? The planner still executes the operator without complaint. After the robot picks up red box, the state still says the hand is empty, and it still says red box is at the dock. So picking up blue box also looks legal. Now the symbolic state says the robot is holding red box, holding blue box, and still has an empty hand. A box can even appear both in the robot's gripper and still on the floor. Physically impossible. Symbolically accepted. Strips does not save you from a bad operator. If you omit a delete effect, the planner will reason perfectly from false premises. 3 operators are enough for this whole warehouse. Pick up, move, and put down. From those 3 schemas, the planner can generate every concrete action the robot is allowed to take with either box in either storage zone. Using those operators, the planner finds a 7-step solution. Deliver red box to storage A, return to the dock, then deliver blue box to storage B. That is the power of strips. The rules stay compact, but the planner can still reason over complete state transitions automatically. The full representation chain is now in place. A planning state is the set of facts true now, and the goal names the facts that must become true. A strips operator is a transition contract. It specifies when an action is legal, and exactly which facts are inserted or removed when that action fires. Once those operators are grounded, they generate a state space. Even this small warehouse already expands into many legal action branches. That creates the next search question. Should the planner expand outward from the initial state, or start from the goal and regress toward the required predecessor conditions? In the next video, we compare forward progression with backward regression. Same domain and same operators, but one direction filters irrelevant action branches much earlier.